And then I'm going to share the screen with you guys. And I'm going to go to full screen here, slideshow on the PowerPoint. Why did it not do it? Come on. Oh, there it is. Okay. Right. So again, yesterday we talked about how a change in flux, right? If I can go back a slide. Is that the slide? Yes, right? The change in flux produces, right? The change in flux produces an EMF and therefore produces a current in a loop of wire. This is the formula here. I looked it up in your on the what's it called? On the formula sheet, the N is not there, right? So on the formula sheet and all the other things, it's always assumed it's a single loop of wire, not multiple loops of wire. So the N is not there on the AP formula sheet. Okay. All right. But the change in flux, the rate of change in flux produces an EMF, which therefore, right, that voltage, that potential difference then produces a current in a loop of wire. And we saw that in the video. What we didn't see is how we decide what direction the current is going to go. So that's Lenz's law, right? And we'll watch a video again on that one also. But the idea here is essentially that the current is produced in a way that the current, because it's a current, it produces its own magnetic field, right? So the magnetic field that the current produces opposes the change in flux. I always kind of think of it as inertia, quote, inertia of, and it helps me think of it this way, inertia of magnetic field. So if I change the magnetic field and I add extra magnetic field lines through, say, the loop going down here in the, oh, I'm pointing, you guys can't at home can't see because I'm sliding the shade on slide, sharing the slide. But on big picture A, if you can imagine taking that magnet and pushing it down through the loop, we're adding more magnetic field lines through that loop. So that increase in magnetic field lines, the current is going to make its own magnetic field to oppose extra magnetic field lines. So the current's magnetic field would go up instead of down, up to oppose and cancel out those new ones. So therefore, the current would be going in the front of this loop, the way the picture is, to the right, and then go around and at the back of the picture to the left, right? If you could think of the right-hand rule, right? That first right-hand rule, my fingers would have to go up inside that loop, right? Because I'm adding extra magnetic fields down inside the loop. So the current's going to have a magnetic field lines that are going to go up and balance out those new magnetic field lines, right? Dylan is looking at me and his eyebrows are crinkling together like I have 3 heads while I'm saying this. You not feeling it? Maybe the video can explain it better than I can. Let's try that. All right. If not, we'll see if we can come up with a different way. Okay. Are you guys at home seeing the video? Because these guys here are not.
No, I can't see it.
You can't see it? If I move it onto the screen here, can you see the video?
You're not. No, I can see it.
So yeah, yes. You can? Okay. Let me go back to the beginning here.
Right over here, you did a square loop of stationary and sitting in a magnet. And I've drawn a few vectors that represent the magnetic field. See, at least on the surface that is defined or that is contoured by the wire, where the magnetic field runs. We just have this scenario, nothing too special going on, but it becomes interesting if I were to actually change the flux going through the surface. So both of these pictures right over here, they actually show the same scenario where we have increased the flux. We have increased the flux with weights on the surface defined by the wire. At every point, the magnetic field is now stronger. So we have increased the flux. We write that flux is 3 letter 5. Flux of the magnetic field. Flux of the magnetic field has gone up. And we know from Faraday's law that when you have a change in your flux, that's going to induce a current in the loop. And so the interesting question is, what direction is that current actually going to go in? We have two options. The current could go, the current could go in the clockwise direction, or it could go in the counterclockwise direction. So which of these two do you think the current will actually go in? Let's think a little bit about it. We know that a current flowing through a wire actually on its own will induce a magnetic field above and beyond the magnetic field that's already there. So let's think about the type of magnetic field that this orange current would actually induce. So if it's going in the counterclockwise direction, remember we use the right hand rule. I can take my right hand, point my thumb in the direction of the current. So let me see if I can do that. So my thumb in the direction of the current, and then my hands are going to loop, or I should say my fingers are going to loop in the direction of the magnetic field. So when I do that with my right hand, so my right hand looks something like that, thumb in the direction of the current right over here, we see that it shows a magnetic field being induced that would wrap around like that. Or if we were to show it, if we were to sample it points right on the surface, the magnetic field that would be induced would look something like this. And I'm just doing it at some sample points. So notice, it would be additive. It would be additive. Whoops. It would be additive to the existing magnetic field. In fact, it would increase the flux even more. In fact, at these points, these vectors would increase even more. These vectors would increase even more. But what would that do? If the flux increases even more, then the current is going to increase. The current is going to increase even more, which is going to make the flux increase even more, which makes the current increase even more. And you would have this never-ending cycle where the current keeps increasing and the flux keeps increasing, and you would have this energy that's appearing out of nowhere, which would violate the law of conservation of energy. And so that's a pretty good argument for why you would not. That's a pretty good argument for why we would not expect the counterclockwise scenario. We would not want the current that's induced to induce a magnetic field that goes in the same direction as our increase in flux. So just by deductive reasoning, we know that this is going to be the scenario. And let's see think about what happens here. We can do the right hand rule again. We take our right hand, point our thumb in the direction of the current, and we see if we do that with our right hand, well, now this would induce a magnetic field that would decrease the flux. So it would produce a magnetic field. The current right over here would produce a magnetic field that's going downward. The current in that direction would also, when you take your right hand and you were to put it along here, so again, if you are going in the counterclockwise, if you're going in the clockwise direction over here, that too, when you do your right hand rule right over here, your fingers would coil around that way. And so once again, when you look at the surface, it would induce a magnetic field that is going in that direction. And so it would have the induced magnetic field from the induced current will go against the change in flux. And this makes sense because we won't go into this never-ending positive feedback loop where the current keeps getting stronger and stronger and the flux keeps increasing and increasing and increasing. And this idea that the orientation of the current that is induced will produce a magnetic field that counteracts the change in flux. This is Lenz's law. Lenz's Lenz's law. And once again, if that wasn't true, then you would have a violation of the conservation of energy. So in general, whenever if someone says, okay, well, this is the change in flux is happening in a certain direction. Well, to think about which way the current would flow, you just have to say, well, what type of a magnetic field would each direction of the current produce? And that magnetic field should go in a direction that goes against your change in flux. So if the flux is increasing, the magnetic field that's induced by the induced current should make the flux decrease. If the flux was decreasing, then the induced magnetic field by the induced current should make the flux decrease less, or it should make the flux should be additive to the flux.
Okay. So therefore, right, so he said it a lot better than I did, right? But the idea,
That's something
uh-oh.
interesting going on. I have this ring of conductor right here, this square ring.
Sorry, it just automatically goes to the next video if you don't turn it off, right? But again, so the idea is, right, that the induced current balances out or kind of produces a magnetic field that opposes the change in the flux, right? Did that help? That video was a lot better than my talk. Dylan is nodding his head that this guy's a lot better teacher than I am. That's okay, Dylan. I'll keep that in mind. I'm kidding. I'm kidding, obviously. All right, that's why I put the video up there, because I knew it was a better way of doing it, showing it. Okay. Any questions? I don't remember I looked them up yesterday and I didn't look at the examples. We can come back to the examples that are in the textbook a little bit later, but let's finish our notes here. Okay. So let's go to the next slide. Is that the next slide? I feel like I skipped a slide. There it is. Okay. So this is the same concept that we just dealt with Lenz's law. It's just instead of moving the magnetic field to change the flux, we're moving the wire to change the flux. So if you can imagine, right, in this picture, know what? I'm gonna stop sharing so I can physically show you guys this. All right, so I can be on here instead of trying to have you guys visualize it just through my description. Okay, I'm gonna turn the lights on in the room. I turned them off for the video. Okay, same idea of inducing a magnetic flux. It's just a different formula to get there. Right, this time the induced voltage is the magnetic field, which is the magnetic field is constant, times the length of wire, times the velocity that wire is moving. Okay? So, imagine here in this picture here, right, that we have two metal conductors along the top and the bottom. Okay? And this metal conductor, inside these two metal conductors, each of these two metal conductors have a current running through them, right? In this case, it's drawn the current through the top metal conductor is to the left, the current to the bottom metal conductor is to the right, okay? And inside the metal conductor, in between the metal conductor, these currents are producing a magnetic field, and it's a constant magnetic field because this conductor and this conductor, those wires, are producing a magnetic field, right? Magnetic and right-hand rule says currents this way. Why is it going that direction? The current should be out of, I don't know why the picture is into. All right. Okay. That feels backwards to me. But we'll go with what it says, right, for our picture. But the point being here, right, these induced EMF and the induced current happen because of a change in flux. So this is another wire. Imagine that as another wire. And it starts over here. So if we can imagine, our flux is the amount of magnetic field going through this area, right? So as this wire moves to this position, the flux has increased, right? The flux is increased because there's more magnetic field going through a bigger area. Okay, so if we have a change in flux, we have an induced current, right? So therefore, again, the way this is drawn, if there's more things going into, right, we just saw this current is going to counteract that increase into the board with a current this direction in this wire that is coming out of the board. Okay? So the induced current through this wire is up. Okay. Where does this equation come from? The BLV, right? So, right, the magnetic field is what it is. The L is the distance that the wire has moved. Oh, that's wrong. I apologize. The L is the length of this wire. The length of this wire, that's L, right? That's L. I'm going to write it in cursive. And velocity is how fast the wire is moving. V is the velocity of the wire, right? But what do we know? We know velocity is change in position over time, right? So instead of writing it as V, I'm going to write it as change in position over time. Now imagine this length times this change in position, right, is length times width. So this is area, right? So now we're at magnetic field times area over time. And magnetic field times area is flux, right? So by moving this, I'm changing the area. And as the area changes per time, that's a change in flux, and that's the induces that current in it, and induces that EMF, that voltage that makes the current. Okay, so this formula is the same formula that we had before for that induced current, that induced voltage, right? The formula we had for 4 was E equals change in flux, right? Change in flux over time. And that's what this is. It just looks different, but it's the same, right? Because flux is magnetic field times area, right? Which, as we just said, that's magnetic field times area over time, right? The rate of change in flux. So it's just a different, because it's a different scenario. It's just it looks different, but it's the same. Okay. Okay. So our last 2 slides here are, I'm going to do demonstration first. Where's my thing? So this is a hand generator. It's an electrical generator, right? So inside the generator, right, I can spin the wire. I can turn this handle, inside the generator is a magnet and a coil of wires. So as I spin it, the magnet moves, causing a change in flux or in this coil of wires, and therefore induces a current in the coil of wires inside, and which we can see now, right? Our plug here. I have a couple of little blue Christmas light bulbs on the end, right? So as I spin this, I don't know if you guys can see it well. I don't know if you guys can see it even here. The light bulb's light, right? And that's how a generator works. It just spins a coil of wires in a magnetic field, or it spins a magnet around within a coil of wires. But either way, either the coil's moving or within a constant magnetic field, or the magnet's moving, either way inducing a current, right? Relative speaking, the same thing's happening, right? And when we actually apply this, right, we can generate electricity. And it kind of works the other way too. If I go, I don't know if I can hold this together here. If I put these two little hand generators together, I don't know, I think I might need a third hand to do this demonstration. Okay. Okay, I'm going to need to get the wires out of the way so they don't, I can spin them. All right, right, I connected the two ends together. So as I spin one, uh-oh, my other generator busted. So I spin one, you can see that the other generator, the handle spins, and I don't know if you can tell, but it spins in the opposite direction, right? So why is that happening? I'm inducing a current. I'm inducing a current. That current then goes here, and then that current, right, induces on the other end, is then used to do the opposite, and which ultimately spins the magnet, which then is attached to the handle, the other direction. Again, I'm inducing a current this way. So now the same exact thing's happening inside the magnetic field over here in the opposite way, because it's got to counteract the new induced current over here in the opposite way. We get that going the other way, right? So this is an electrical generator, and effectively this is an electrical motor. This uses mechanical energy to make electricity. Here I'm using electricity to make a mechanical energy. But notice the opposite directions because of that Lenz's law, right? Does that make sense? We okay with that? All right, so that's what the next and last two slides are. All right. Our last two slides are, this is an AC generator, right? AC means, right, the current kind of just goes back and forth, that the electrons within the wire don't go in one direction. They go one way and then they turn around and go the other. So essentially this is, if we can imagine this here, right, there's a constant magnetic field, and this is our loop of wire. So as the loop of wire rotates, and in this picture, the rotation is counterclockwise. So the way it's oriented right now, there's zero flux because the loop is parallel to the magnetic field. So as it turns counterclockwise, the flux increases to the point where it gets perpendicular. So an increase in flux this way, right, would induce a current. So as this goes to here, I'm getting more. So it's going to induce a current using my right-hand rule that's going to go from the back to the front through the blue section of the wire. Right, can we kind of visualize that? But now that the loop is at its max, as it continues to rotate, it's going back down to minimum where it's going to be parallel with the magnetic field lines. So going from the maximum flux down to the zero flux, now I'm having less and less magnetic field lines through. So I got to increase the magnetic field lines, more magnetic field lines through the loop, which means that the current's got to go in the other direction. Right, and that's what produces a AC generator, is this continuing going from zero to maximum. So it has to induce the current one way, and then from maximum back to zero, induce the current back the other way, and so on and so on and so on. Right, and then we get a AC, right, AC, right, back and forth and back and forth. That's how a generator works, an AC generator. That's what we have coming to our homes. That's what we have, right? A DC generator, which is this thing, is a DC generator. It works the exact same way, but the difference is there's a gap. So like, see these things here, these called brushes, these carbon brushes? They effectively, these two wires, the red wire and the blue wire, are touching the carbon brushes, causing and allowing the current to go through these, and these go out to the, right, this is your conductor wires conducting out to the grid. In a DC conductor, the exact same thing's happening, except there's these little gaps in the brushes. So as it goes from minimum to maximum, we get the current in one given direction, but then it skips. So when we're at maximum, and the wires continue to go, they skip a period of maximum to minimum, right? Because there's no connection, so it's a open circuit. So minimum to maximum, the wires produce a current. Maximum to minimum, there's no current, not because of the induction, but because it's an open circuit. And then it starts over again. So it's always minimum to maximum, minimum to maximum, minimum to maximum. So it only goes in one direction. Right? Now, technically, there's a pause in the current, right? There keeps being a pause in the current. But if you spin it fast enough, that pause is such a small period of time, it becomes negligible. But so that's a DC generator, the same concept. Right? Okay. Any questions on what we covered today? There are two examples. I forget what they are, to be honest. So let's take a quick look and see what they are. Page 590. Page 590, example 21-12. See figure 21-12, page 590. Do example or exercise C. In what direction electron flow in this if the rods move to the left, decreasing the area of the loop? So it's this picture, except instead of the area increasing, if we move the wire to the left and decrease the flux, what would the direction of the induced current be in that wire? Right, so it's the exact opposite thought when we went through it. If we're decreasing the flux, then the induced current is going to counteract that decrease in flux and increase it. So there's less going that direction. So the current needs to add more in that direction. So the current's got to go down this wire that's moving. Right? There's We have less and less going into the board. So the induced current's got to add back and counteract that loss of magnetic field lines by adding more in, so the current's got to go down. Right, and that's what the picture is in the book for that example. 21-6. In the airplane traveling 100 or 1,000 kilometers an hour in a region of space, the magnetic field is 5 × 10⁻⁵. It's nearly vertical. What is the potential difference between the wingtips that are 70 meters apart? So it's just a plug and chug into this equation, right? We don't need to do that. You can just plug and chug into that. That's simple enough, right? You guys are all intelligent. You need me to do an example where I'm just plugging and, you know, taking numbers and plugging and chugging. Okay. Any questions on anything that we just covered yesterday or today? All right, so you have about 10 minutes or so if you want to get started on your assignment. I've asked you to do the, there's, you know, on Schoology, there's questions and problems out of the textbook. I would like you to try and do them over the weekend, right? Like I said, we're a little bit behind. Most of them are just, or about half of them are just figuring out, using Lenz's law and figuring out what's the direction of that induced current in this loop. What's the direction of that induced current in that loop? So about half of them are just conceptual, not even using the formulas. All right, I'm going to stop recording now, Sammy, because we know